Hello everyone, this is Mr. Kaviani, and by the end of this video you should be able to describe the relationship between the net torque exerted on an object, its moment of inertia, and its resulting angular acceleration. And you should be able to use this relationship to solve problems involving torque and rotational motion. All right, now if you recall from linear motion, we saw that forces were the reason that objects accelerated. And in rotational motion, we've explored how torques are the cause for rotation, right? When you apply a force a certain distance away from the center of rotation of an object, also known as its lever arm, we're able to create a torque that is responsible for causing that object to rotate or to angularly accelerate. And so earlier, we saw there was a relationship between the net force, or the sum of all forces on an object, and its acceleration, also given its mass. This relationship we called Newton's second law. And we saw that the linear acceleration of an object was directly proportional to the net force on the object. So in other words, when you increase the net force, you also increase the acceleration, and inversely proportional to the mass of an object. So if you make an object heavier and you apply the same net force on it, it's not going to accelerate nearly as much, right? So that should be make the mass bigger, acceleration gets smaller. There we go. So we can actually define a very similar relationship for rotational motion. In other words, Newton's second law in rotational form. And instead of force, right, we're dealing with torque. So we're going to say that the net torque, so tau net, the net torque on an object is proportional to, right, the product of not mass, but we saw that in rotational terms, mass can be replaced by I, moment of inertia, multiplied by not A, but alpha. And if I rearrange this expression for alpha, I can see a similar relationship. And so I see that just like linear acceleration, if I were to increase the net torque on an object, so if I increase the torque net, I will also increase my angular acceleration. So if I apply a greater torque, I will cause an object to increase the rate at which it is increasing its speed, its rotational speed. On the other hand, if I were to increase the moment of inertia, like for example, let's say I distribute the mass of that object farther to the edges of that object. So I were to, take that mass, maybe I can, rearrange the mass of this object and I can move it out farther from the center. If I increase that moment of inertia, I'm going to decrease the angular acceleration. And so we said that moment of inertia was the tendency of an object to resist accelerating angularly. So if I increase I, I'm going to decrease my angular acceleration. It will become harder for that object to rotate, and it will not accelerate as greatly for the same net torque. All right, so we're going to use this relationship, this Newton's second law in rotational form throughout the rest of this unit. And in a moment, we'll solve some example problems using this new relationship.